not sure how to do that. And additionally, again, to explain before we get going, we will have some Q&A during the presentation as well as afterwards, and that will be in the Q&A chat feature. So you can actually just chat in your questions while we're while we're talking, and then at the given Q&A times, we'll go ahead and read them out loud, and myself or Gay Stewart will answer them. So I'm seeing nobody chat in any questions right now as far as like technical difficulties. So we'll go ahead and get started. To introduce myself, my name is Tommy Mena. I'm the STEM Marketing Manager at BFW. So I'm hosting this webinar, but the webinar is being presented by Gay Stewart. So real quick, before I pass it over to Gay, I would like to say thank you. So thank you, Gay, for your time. And I believe there's some echo. Everyone can, again, mute themselves. I'm getting some feedback, sorry. Yeah, if you could just... Speaking about clear language and everything. And before I pass it to Gay, and Gay, you could say hello if you're on. I don't know if you're there yet, but Gay has recently won AAPT's 2019 Orsted Medal, so be sure to say congratulations to her if you can. But without further ado, I will pass it over to her, and we'll get this going.
Hi there. Can you hear me?
Yep, we can hear you.
Oh, excellent.
So I believe we will give you control, and now you can share your screen.
Did it work?
Yep, you should be able to share your screen now.
Okay. Can you guys see that?
Not yet.
Okay, let me... So I've got it up on my screen.
Do you see an option if you hover to share your screen, Gay? There we go.
Okay, I'm sorry, guys.
All right. So.
Thought I had it and didn't quite. I promise the rest of the talk will be better.
All right.
So I wanted to talk to you a little bit tonight about how important the careful use of language can be in helping promote problem solving, particularly in the AP Physics. That was the description, you already saw that. So I thought I'd start out a little bit with why me? Why am I here? I've been an advocate for physics teacher preparation and support for in-service physics teachers for over 20 years. And I mention it because of this animation that I'm going to subject you to in a couple of minutes. Recently, a grant was funded that includes national change agents for support of physics teacher preparation, and the program officer made a crack that it just made him think of me. He wasn't sure why. But the other reason I'm here tonight is because of my, my long history with AP. I started out on the AP Test Development Committee back in 1997. I chaired the College Board Science Academic Advisory Committee for a little over a decade, including being chair for 6 years. When we were first pondering the AP Physics redesign, the College Board contracted with the Center for Educational Policy Research to do a college curriculum study, and they formed a physics calibration team. And I got chosen to be part of that, which was kind of cool. I mean, the calibration team, the members were nominated by the College Board and its committees and professional organizations. But the course validation panel, you know, I kind of thought I'd be on the first one, but then I got nominated for the validation panel, and that was by a bunch of stakeholder organizations. So I was pleased that I got to participate in that. Then I was chosen to be a co-chair for the AP Physics redesign. And following the redesign, there was a peer review panel, which obviously I wasn't part of. But then we had a review advisory panel where the peer review panel and
the co-chair of the redesign.
Redesign folks got together and planned something.
But right now they're just doing introductions, so I'm not.
If I could jump in, I think some people, if you could just mute yourself. Sorry, I think it's causing some feedback. Thank you.
Yeah.
Sorry.
And so then I was on the Curriculum Development Assessment Committee, which actually took the framework to generate the course and the assessment. And I got to be co-chair of the AP Physics 2. And the thing is, so I've been involved in this process for over 10 years. And when I saw, you know, sort of repeated information that teachers didn't feel like they had the resources to support them in the careful language, the deep conceptual construction of the course, I was, you know, it was bad. I felt really bad about it. And so when FBW came and said, you know, if you'll work on this textbook, we'll put together a team of expert AP teachers to develop the resources that teachers say they need, I had to say yes. There's the animation I threatened. So the thing that caused this careful attention to language is actually a study that came out from the National Research Council, which reflected what we knew from physics education research. And this came out in 2002, just as I was kind of wrapping up on the AP committee and starting on the academic advisory committee, that there are opportunities to improve the way math and science were taught in the United States. Their focus was on advanced study in high school, AP and IB, but they pointed out that, you know, anything they found wrong with those, it was what was wrong with the introductory college education as well. That introductory college courses should emphasize deep understanding rather than comprehensive coverage. The program should reflect current understanding of how people learn in the discipline. It'd be nice to help kids make connection to research in the discipline so they understand why it's interesting. And that the courses really need to include a strong emphasis on inquiry and reasoning. You know, from the research, I'm somebody who does research in physics education, and my time working on AP and with AP teachers, I knew this was really a fantastic opportunity for us to move AP forward. So what I'm going to do tonight is give you some examples of simplified statements that can lead students to misunderstandings. I'm going to present 4 of the biggest culprits and the misunderstandings they cause, and then I want to go back and unpack those misunderstandings one by one. A recurrent theme you'll find if you look at the chief reader reports for the new AP Physics 1 exams is that students need an opportunity to practice written justifications, but that they really need to practice using correct physics terminology And teachers need to be precise in modeling that for their students and encourage their students to be precise in the language, and again, give them lots of opportunity to practice explaining things. So this focus on language seems kind of important. I do want to mention, please feel free to ask me questions at any time. Tommy will pass those along. So my first example of a simplified statement, and we've all seen this in a textbook or a problem. Somebody will ask about the potential energy of a ball, or it could be a sphere or whatever. But this really does lead to misunderstandings for the student. Potential energy is a property of a system. So if you're using an object model for a ball, if it's just a thing, it cannot have potential energy. And using this language it misses out on that opportunity to support an understanding of why and when you would use work or potential energy. The thing is, you just know it or you don't, right? If you've been in physics a long time, you've heard it all, but you know what that means, that you're talking about the potential energy of a system, of the ball and the earth. But our students, they hear what we say. Another simplified statement that, and all of these are things I've been guilty of doing, saying work is force times distance. Well, this turns out to lead to some misunderstandings as well. What distance? Is it really clear when you say that this has to be an external force to use a definition of work? And in saying it this way, it really doesn't understand that depth of understanding of the definition of work. That work is always something that's external to a system that can add energy to a system. And so we end up, kind of feeding our students out on building that understanding and giving them a way to check themselves when they do problems. Oh, this one is really hard to wean yourself of. Forces act on things. We say that all the time. It's in the chief reader's report from the last exam. But when I saw the results of the research, what students actually think forces are, I realized that this really does lead to misunderstanding. Students think that forces are a thing that exists by themselves, right? Because they're an independent actor. They're acting on stuff. And, if they have this confusion that a force is a thing of itself, then, again, when you're thinking about work, it makes it harder for a student to go back and think about where is the energy coming from, checking their answer to make sure it makes sense. And I wasn't going to throw any of these in yet, but there's an example of an AP Physics 1 problem. This one, you didn't even have to use energy to solve the problem, but because the students are less careful at thinking about what's causing a force, the students ended up losing points on this problem. One of the major problems was actually drawing forces that didn't still exist when they were asked to draw the free body diagram. And then one of my biggest pet peeves, we hear this all the time, work is the negative of the change in potential energy. But if you just say that, if you just write that down, it leads to some misunderstandings. Usually when students see an equation like that, you think about both those things at the same time or somehow being equivalent. So they start thinking that both of these things are happening at the same time. If you convince them that they're not, then it's not clear to them which one of those things that they should use. And again, it turns out to be one of those things that you just know or you don't know. And this one in particular even leads faculty into difficulties. One of my favorite stories, a friend of mine at Harvard went around and asked his colleagues a question related to this, and many of them actually started out wrong. And then they caught themselves, but they immediately, caught themselves, oh, no. But if it's a student who hasn't had that years of practice, how are they going to tell that what they're thinking isn't quite right? That's the thing I worry about. So the thing I'm going to do now is start unpacking some of these statements. And again, please, if you have any questions, jump in. So potential energy is a property of a system. That means objects cannot have potential energy. By definition, you can't change an object's shape. You can change the shape or the configuration of a system that's made up of more than one object. This is a foundational idea in both Big Idea 1 and 5 of the curriculum framework. And one of the nice things about potential energy, if you stick with this idea of systems, is you can develop the concept starting with things that you can change the shape and feel it, right? So you squeeze a ball or you stretch a spring or a rubber band, you let it go and it changes back. And the more, springy it is, the more it looks like it started out. And that's a great place to start developing the concept of potential energy. And then you go to gravity. Well, your system is the Earth and the object, and you pull them apart and you let them go and they go back together. So potential energy always depends on a configuration, and if you can't change its shape, it's not potential energy. So it can't be an object. Also, it's important to support students' understanding of why and when to use work or potential energy. So if you always start by defining the system, putting in all the words we tend to leave out to make it easier to say, then it's actually clearer to see what thing you should be using. Right? Potential energy is always something that's internal to the system. It always depends on the shape. Right? So if you can't change its shape, can't change its configuration, it can't have potential energy. If I'm talking about a ball, and what I'm thinking about is gravitational potential energy, then I'm changing the shape of what? Oh, it's got to be the Earth ball system. Now, if I have a ball that I can squeeze, if I can't, if it's not something I can model as an object, then it could have elastic potential energy. On the other hand, if I have just a ball, and I'm thinking about the interaction with the Earth, if the Earth's not in the system, it's external, so that's an external force, and we would use work. How much energy is Earth, which is outside the system, transferring to the ball, which is our system? That was actually understanding when to use work or potential energy with something that can lead to a problem. For instance, in this one where students had to do both those things, using potential energy with the spring and then work as the thing slid across a frictional surface, and students had trouble figuring out which distance went with what and what they were trying to do. So, which leads us to what distance, and is it clear it has to be an external force? So if we stick with our careful definition every time that work is the transfer of energy into or out of a system by something external to the system, the idea that anytime we talk about an interaction, one way to describe an interaction is a force, and if that interaction is with something outside of a system, then it's an external force. then we can start understanding what our distance has to be. It's how far the point on the system on which the force is exerted moves in the direction of the force. The thing that gets kids confused sometimes is that we often throw out this definition that if you look at how far the center of mass of the system moves, it's times the force. That gives you the kinetic energy change. But the center of mass and the point you're pushing on don't have to move the same distance unless you're talking about an object, right? Because our definition of an object, again, is that every point moves the same distance and in the same direction. So if we have something that's rigid, something we can model as an object, when we push on it, the only thing we're going to change is its kinetic energy. And the thing is, if we go back, we're always careful with our language, then every time we talk about one of these things, we're supporting that deep understanding of the definition of work, something that can add energy to the system. And you know, we can actually use repeated examples to think about, talk through where the energy has to come from, if it makes sense that it should be work or not. For instance, when a rubber ball bounces off a wall, right, the wall doesn't move. The point of contact of the force doesn't move, so the wall doesn't do work on the ball, which makes sense because you could set a ball next to a wall all day and it's not going to go flying off. It's the fact that the ball squeezes up against the wall and then bounces off. So that wall lets the ball convert its own energy from kinetic into potential and then back into kinetic. Another big misconception is students will think that when you run, the ground does work on you. But we know we can stand on the ground all day and it's not going to move us. So it's a great place to talk through Newton's third law as well as work. You push on the ground pushes back on you. The point of contact isn't moving, so it's just letting you convert your internal energy into kinetic energy. In fact, if the point of contact does move, it tends to slide and then actually you lose energy. Talking about where the energy comes from and goes when a moving ball of dough hits the ground. Right? The center of mass moves as the dough squishes out, but the point of contact doesn't move. So there's no work done by the ground on the dough, but the initial kinetic energy of the dough turns into squishing the dough and making noise. And carefully thinking through these energy transformations is actually a great way to help kids think about how to track down the energy, which was a particular problem with some of the most common errors on the first problem on the 2018 exam, which was 2 blocks connected to a spring, and the students had to argue about where the energy was going. They had a lot of trouble understanding when energy should be constant, when the mechanical energy of a system would be constant, and they ended up getting like less than 1 point out of 7 on that problem. Oh, I guess that was problem 5, I'm sorry. Oh, sorry, is there a question?
Yeah, I was just going to interrupt real quick to let folks know they can, there is a chat feature, so if you do have any questions, you can just write the question in the chat feature, and then that way I can then ask the question to Gay, who can answer it.
Please ask questions.
Anyway, back to you. Sorry about that.
Oh, no, please. Yeah, do ask questions. I don't like to lecture, and this is feeling an awful lot like a lecture. So if there's any questions, stop me.
Yep. Yeah, if you just put in the chat feature, I'll interrupt and ask the question. But with that said, back to Gay.
Okay. All right. I guess the next thing, the one I said was really hard to wean ourselves of, that a force acts on things. If we always emphasize that a force is one way to describe an interaction between the objects and the system, that it's always exerted by one object or system on another, and always identify both those things when we talk about a force, then if we see that both the thing causing the force and the thing that's exerted on it in the system, then if the interaction only depends on the shape of the system, we can talk about potential energy as a conservative force. Developing this from a focus on potential energy, the idea that potential energy is tied to the change in shape, and if you have the same change in shape, you get the same change in energy, makes it a lot clearer to the students what these words path independence that we use when we talk about conservative interactions means. And that was one of the things they really struggled with on the problem 4 on the 2017 exam, and which was blocks going on ramps that had different shapes. Even though the students knew to say that potential energy was related to height, and so they got about 2 points out of 7, they struggled with the idea that what they wanted was the change in the potential energy and how that related to what they were seeing, because they were literally just doing MGH instead of thinking, potential energy of this ball at these different points, instead of thinking, I'm changing the shape of the system, how much did that change happen? So it led them into some difficulty. So when thinking about work, if the force is a thing, where does the energy come from? I think we pretty much kind of unpack that one when we talk about all the things we already talked about. When you're really thinking about what it means to do work, that it's an external force, and that external force is exerted on an object or system, and it moves that object or system, it's a little easier to keep it clear. And it really does matter about helping students to understand what's causing the interaction, and then what kind of change in energy that's gonna involve. And this was something students had a lot of trouble understanding, which interaction caused what sort of change. And problem 1 in the 2016 exam, which is a wheel on a ramp, and they were trying to figure out, what the frictional force was doing and the normal force, and they didn't do a very good job associating those with the kinds of energy, what was going on. So actually the last thing I was going to talk to you about, so I hope you have some questions, but I am going to beat on this one for a minute, because even though I'm actually ending on this one, it's what started me into this area of trying to understand how people learn physics. When I was a relatively new faculty member and I volunteered to help out at a local school, I ended up, I'd never done professional development for 6th grade teachers, and they were teaching the same stuff I was teaching in introductory college physics, which was totally wild. So I asked them what their favorite activity was, and they showed me, and it was a roller coaster. And they had gravitational potential energy and work due to gravity, both in the example. But because they never calculated a number, they never noticed that there was a problem. And because they had never thought about defining the system, they didn't understand why only one of those was appropriate. So if you always start with defining a system, you always know which one of those things to use. And you always think about work as the mechanical transfer of energy to an object or system by another object or system that's external to it. And potential energy is always a change inside a system due to an interaction in the system that only depends on its configuration. And again, that's important. Even though you can always call an interaction a force, I really like emphasizing the idea of an interaction and saying, you know, when I want to call it a force, it's always an interaction. It can be described by a force if I want to. You can call these internal forces, but just to help, you know, if you bring that up, drive the students crazy, but you help them understand and make that clear distinction in their head. And you end up getting lots more good descriptions of what's going on. Okay. Good.
And if we could remind everybody, there is a chat feature, and Gay is taking questions now. So if you have any questions, be sure to address them in the chat feature, and we will ask them out loud so we can get them answered. If you see on the screen here, we do have a, if you look at the purple lines, that kind of shows you how to open up the Q&A chat feature. Check that out. And Gay, thank you so much. Really good. I do have one question to get things going while hopefully some other folks enter chat in some more questions. But, and I know we just talked about all of this, but could you maybe go over a little bit more how you would, you know, how you suggest students discuss positive and negative work?
Yeah, because that's something that tends to get kind of confusing for students. And, you know, because we talk about the work done on a system or the work done by a system, and, you know, was that positive or is that negative? But if the students in their discussion are always careful to say whether work increases the energy in a system, and then that an energy that if the work done on a system increases its energy, then it's a positive work. And if the work done on a system decreases its energy, it's a negative work. That gives them a way to make sure they're going to get full credit, because that's the important thing we're looking for. But they can also check their signs and make sure they didn't do anything, you know, dumb in the math. So this idea of work done on a system increases its energy, or if you do negative work on a system, you decrease its energy. It's a really important idea.
Great. And one other question that came in was real brief, is sort of, are there any other misconceptions a student could have as far as, you know, this type of, speaking about this type of work?
Yeah, students have, well, a lot of misconceptions about energy. Some of those that you can help mitigate just by constantly going back and using kind of consistent language. The other thing, the thing students tend to think, sort of a misconception, they will approach every problem that has to do with energy like it's a different thing, because they learn the tricks instead of really understanding what the whole thing is. Okay, so I've defined my system. This is what's important. The way they get around not actually understanding how it grows up from defining the system is they will just memorize all these different things. And so there's this kind of problem and that kind of problem. The other thing that will cause a kind of a trap even for really good students is the idea is friction, because friction's weird, right? Friction is a way to describe an interaction between two surfaces. The friction's only going to exist as a force when something is trying to push those surfaces past each other. So it actually isn't the same thing as any other force that we talk about when we talk about work. Because the actual, you know, if you increase something's energy through a frictional force, there's got to be something else that's pushing it. You could think about, you know, walking on a treadmill, or more importantly, standing still on a treadmill that's running, right? So if there's friction between you and the belt on the treadmill, it's going to, you know, start you moving until it throws you off the end. There's not, you know, but there's a motor generating that motion. So there's still something external that's putting energy into the system.
Great. Well, I do have the chat feature open a little bit more, but I guess no other questions are coming in. So again, I would like to take a second to say thank you, Gay, for your time and attention and, you know, giving up your evening to talk with us about this topic. It was hopefully very helpful for everybody on the line. And now we're going to enter the part of the webinar that I call the shameless plug portion of it. Because if you haven't figured out already, Gay Stewart is the lead author of our new College Physics for the AP Physics 1 course textbook that is coming out. So some quick housekeeping things. I put my contact information up there as well. If you come up with any questions, or if you would feel more comfortable emailing me a question about this, you know, about the book or about the webinar we just had, anything at all, please don't hesitate. Also, my PD manager, Tracy Wegleitner, that's her email right there. If you need a PD certificate to present to your school or principal, definitely email Tracy and we can go ahead and get you one of those. And finally, we can share these slides with you that Gay went over. So if you are interested in those slides, just send me an email, or I can reach out to the participant list and get you guys the slides. And finally, one last thing before we go, I would like to quickly share with you that URL that was up there. And this is our College Physics for the AP Physics 1 course microsite, which is up on our catalog, which you can visit anytime, and I definitely recommend everybody takes a moment to do so. When you're here, there's a bunch you can look at. For instance, you can take a whole tour of the entire program. You could look at, you know, everything from the features to the teacher resources, and most importantly, check out a sample chapter of the book. We actually have, believe it or not, the chapters 7 and 8, which are about energy, up there, which was very relevant to the webinar we just had. And we are very excited about this book. Hopefully you are too. You can see we have a ton of AP-specific content, sort of AP exam tips throughout the book. We have additional AP skills practice built into the features. And then what's really cool, which I'm really excited about, is we actually have, at the very end of the chapters, we have AP-specific practice problems, which I'm scrolling fast to get to the bottom of it. But when you get there, you can actually see all those practice problems. We have AP group work included into the program, and here you can see we have a bunch of AP-specific practice problems. So it really is a awesome product. Please go here and check it out. You can also, of course, request a copy so we can go ahead and get you in our system to receive a copy as soon as it publishes early next year. So again, there's the link if you want to go visit that microsite. It's highschool.bfwpub.com //Stewart AP Physics. You can also visit our catalog. Just type in BFW High School and navigate, just click Science, AP Physics, and you'll find your way there. Otherwise, we will send everyone a copy of this recording. Thank you so much for joining us today. And again, thank you, Gay, for your time and effort and presentation. It was very helpful, and I hope you enjoyed yourself as much as we did. And with that, I'll have let everyone have a good night. So thank you.
Thanks, everybody.
All right. Bye, guys.